If you really want to get a handle on where quantum computing might be going,
Yeah.
you've got to look at this truly amazing piece of physics and engineering. Think about it like this. Imagine you're using sonar to track a sub, deep down in a dark, stormy ocean. Usually, right, the echo you get back is just a fuzzy blob. But what if that echo, the returning signal, was so sharp, so focused, it sliced right through the noise, and you can actually read the lettering on the sub's hull, crisp and clear?
Yeah, that's a great analogy, that kind of hyper-resolution pulling a real usable signal out of what should be quantum chaos. That's the core idea in Google's latest work.
Right.
And they ran it on their Willow quantum chip, which has, over 100 qubits.
Exactly. And that's why we're diving deep today. We're looking into their claims about this quantum echoes algorithm. An algorithm, they say, establishes verifiable quantum advantage on real hardware that's actually running. I mean, the sources we look at, they don't hold back. They're basically saying a specific calculation, one that would take a top-tier classical supercomputer they named Frontier years to do. Well, Willow did it in hours.
Right. So our mission today is to really unpack that. We need to get into the physics, understand this time reversal thing that sounds almost like science fiction, and crucially figure out why this verifiable advantage standard is, well, potentially a bigger deal than the older supremacy claims. And, how does this maybe shift quantum computing from just being a lab experiment towards something more like a scientific instrument?
Okay, let's just hit you with the big number up front, because honestly, it frames everything else. We're talking about simulating a very specific, very tricky quantity, an off-diagonal correlator, the estimate. For the Frontier supercomputer, it's about 3.2 years of non-stop compute time per circuit.
Per circuit, yeah. That's important.
And the Willow chip. It collected the data needed for that same circuit in roughly 2.1 hours.
So do the math. That's an effective speed up around 13,000 times. For this one, carefully chosen problem.
That number, 13,000x, that's the anchor for this whole deep dive.
Okay, so let's talk about this shift from supremacy to advantage. Because, there's been a lot of, let's say, healthy skepticism around quantum claims. For years, the big news was always quantum supremacy. But those experiments often got criticized.
Because the problems felt a bit artificial.
Exactly, contrived. They were often designed just to show a quantum machine could beat a classical one, even if the problem itself wasn't scientifically that interesting. And the goalposts for classical machines kept moving too.
Okay, so if the old claims were sometimes like running a race nobody else cared about, how do we know this huge 13,000x speedup isn't just another one of those? Another super specific problem that only Google's setup is good at? What makes this verifiable? What's the real test?
Well, it's kind of a two-part test. First, the problem itself needs to actually matter scientifically. And here, they're measuring something called information scrambling. That's fundamental to understanding chaos, how systems thermalize. It's a real physics question.
Okay, so it's not just a random math problem.
Right. And second, the result has to be checkable. You need ways to validate it. So the new standard verifiable quantum advantage means you run an algorithm, get a result, and you can check that result in principled ways. You have to show that trusted classical methods just can't keep up, not within a reasonable time frame or cost. You can't just wave your hands and say it's complex. You need the data.
And the specific tool, the mechanism they're using to get this verifiable advantage, it relies on these things called out-of-time order correlators.
OTOCs. OTOCs. And they measure them using this quantum echoes algorithm. Let's go back to that pond analogy. You let the quantum system evolve forward. That's like ripples spreading out. Then you give it a tiny nudge, a little disturbance. Now, here's the key part. You mathematically reverse the evolution, like running the film backward to make the ripples go back to the center.
Okay.
And then you measure what's left, the residual signal. That's the echo. And it tells you precisely how far that little nudge spread before you hit reverse.
Ah, okay. So instead of just watching the signal dissolve into noise, which is what usually happens,
Yeah.
this time reversal thing kind of refocuses the important bits, pulls the signal back out of the noise.
That's the core idea. That echo, that refocused signal, it persists. It lasts way longer than ordinary measurements would. Those standard measurements just see things get messy and random. But the echo holds on to the information. That ability to refocus, to pull structure out of chaos, that's where the advantage comes from. Standard methods see fog. OTOCs use time reversal to see through the fog.
Right. But reversing time, even mathematically, in a quantum system, that sounds incredibly delicate. You must need hardware that's just unbelievably stable and precise to pull that off. Yeah, you can't do that with sloppy controls.
Oh, absolutely. The Willow chip, according to the sources, is fundamental here. Think about it. Any tiny error, any bit of noise, any miscalibration in your gates, when you try to run things backward, those errors get amplified hugely.
Like compound interest, but for errors.
Exactly. If your forward step is slightly off, your reverse step needs to be perfectly opposite. If it's not, if it's just, say, 0.9 degrees back instead of 1.0 degree back, that tiny 0.1 degree error builds up step after step after step. Any sloppiness basically just scrambles the very interference pattern you're trying to see. It washes out the echo.
So it's not just that Willow has, what, 100-plus QUIP? It's got to be more than the number. What are the specs? What engineering details make it good enough to run the clock backward like this?
Well, it's a superconducting chip, frequency tunable, laid out in 2D, that helps with connectivity. But the really critical number is the gate fidelity. How accurately can it perform operations? They report median 2-qubit gate errors around 1 part in 1,000, like 0.15%, which is extremely low for current hardware.
Okay, 0.15%. Why is that specific level of fidelity so crucial for time reversal? Couldn't a machine with, say, 1% error just do it slower, or maybe fewer steps?
You could try, but the whole system would likely decohere, lose its quantum nature much faster. The echo signal would probably be way too weak to even measure by the time you finish the reversal sequence. You need the quantum state to stay coherent, to hold together long enough to run the forward part, apply the nudge, and then execute that whole complex refocusing sequence backward. With higher error rates, the information just leaks away before you can refocus it. So Willow's low error rate means it can maintain that coherence long enough to actually build and then refocus these delicate interference patterns. It's like a finely tuned instrument.
Right, so it's maybe less about building a giant general-purpose quantum computer right now, and more about engineering a specific instrument with the right balance. Good size, fast gates, and this incredible control needed for this kind of task.
Exactly. It's about having the right tool for the job. And in this case, the job is acting like a sort of manybody microscope.
Let's dive a bit deeper into that microscope analogy, specifically the constructive interference bit. We have the process: forward, nudge, reverse. And you mentioned they focus on OTOC2. Why that specific one? What's special about OTOC2?
Okay, so it relates to how information spreads in these chaotic quantum systems. When the system evolves, even simple starting inputs become incredibly complex. They spread out into combinations of many qubit states. Physicists call them polystrings. It gets messy fast.
And that messiness, that operator growth, is why classical simulation is so hard.
Precisely. Now, when you reverse the time evolution, you'd expect most of those complicated paths to just recombine and cancel each other out. Mostly. Mostly. But here's the clever part, the discovery. For OTOC2 specifically, certain combinations of those complex spread out operators don't cancel when they recombine. They actually interfere constructively. They add up, they reinforce each other.
That's the echo signal. It's the part that doesn't cancel out, it stands out.
That's it, exactly. It's a clean signal popping up right where you'd expect total chaos. And because it's constructive interference, the signal is strong enough to be clearly distinguished from the background noise. It resists that exponential decay you see in normal measurements. This specific structural feature is why classical methods just choke.
Okay, why do classical methods choke on OTOC2? We're talking about Frontier, one of the world's fastest supercomputers, running advanced stuff like tensor networks. Where does it break down?
The breakdown happens with something called the off-diagonal terms. Think of the OTOC as a matrix. Classical simulation techniques, like tensor networks, are generally pretty good at calculating the diagonal terms those represent, sort of, the overall state at a given time, local correlations.
But the echo, the important information, isn't on the diagonal.
Nope. The really strong part of that constructive interference, the signal you want, it comes from these off-diagonal loop interference terms. These capture the highly non-local, subtle ways that initial nudge rippled through the entire system. Simulating these specific terms, especially with the kind of operator growth you get in these systems, becomes exponentially expensive for classical computers. Classical methods are great at approximating local stuff. They just can't handle these deep, global interference patterns efficiently. It's like they can estimate the blur easily, but calculating the exact interference causing the sharp lettering, that's brutally hard.
Okay, let's bring it back to that 13,000x number again to make sure we understand why it's considered verifiable. What were the specifics of the problem they set up that really pushed classical methods over the edge?
So they chose a specific setup, 65 qubits arranged in a particular way, and they ran deep quantum circuits. They picked 65 qubits because it's right at that scale where it's just big enough to be incredibly challenging for the best classical simulations, but maybe just manageable for their quantum hardware.
And the classical estimate wasn't just a guess, right? They actually tried to simulate it.
Exactly. They didn't just pull the 3.2 years out of thin air. It's based on serious attempts using state-of-the-art tensor network methods optimized for Frontier. They calculated how long it would take Frontier to simulate that crucial off-diagonal part of OTOC accurately, hence 3.2 years per circuit.
Okay. And Willow?
Willow collected the actual experimental data in about 2.1 hours per circuit. So when you have measured quantum time versus a rigorously calculated classical time on a known supercomputer, well, that starts to look like a pretty solid claim. It's not just marketing, it's a documented advantage.
Yeah, and it highlights that key point. Willow doesn't beat Frontier on everything. It wins on this specific task, a task designed to exploit the classical weakness in simulating complex interference. The advantage is located, specific, but seems undeniably real for this problem.
Which naturally leads to the so what question. Okay, it's a great benchmark, but how does it become a tool, a real scientific instrument?
The sources push this idea of it being a manybody microscope, and they immediately outline a workflow using it for something called Hamiltonian learning. This feels like where it gets practical.
Yeah, absolutely. They don't just stop at the benchmark, they show a potential application. The idea is to use the echo measurement to figure out unknown details, unknown parameters of a real physical system. The workflow they suggest is pretty straightforward. First, measure OTOC2 on the actual physical system you care about. Second, run a quantum simulation of that same system on Willow, but make some parameters in the simulation adjustable, like the strength of interactions between particles. Third, you just tune those adjustable parameters in your simulation until the echo signal from the simulation perfectly matches the echo you measured from the real system.
Got it. So the echo isn't just a signal, it's like a fingerprint. You tweak the simulation until it produces the same fingerprint.
Exactly. And what makes OTOC2 really good for this is that the echo signal changes smoothly as you change the parameters. That's super important. It means you can reliably find the best fit. There's a clear minimum or target value. That's what scientists need to confidently figure out the properties of their system.
The paper specifically calls out solid-state NMR nuclear magnetic resonance as a prime candidate. For someone listening, why is NMR such a good fit for this quantum echo trick?
Well, conventional NMR has a fundamental challenge: signal loss, especially in complex materials or big molecules. The signals decay quickly, and the important correlations between distant parts of the molecule get scrambled. This makes it really, really hard to detect weak interactions between spins that are far apart. And those long-range interactions often tell you crucial things about the material's structure or function. Scientists can spend ages trying to nail those down.
Right, and the echoes essentially give them a sharper view, a better ruler.
Pretty much. That time reversal refocuses the dynamics. So those faint long-range couplings that would normally just vanish into the noise, they can reappear as distinct, measurable features in the echo's interference pattern. It offers a potentially much clearer way to infer the structure, learn the Hamiltonian parameters, maybe faster and more accurately than before.
Okay, so we have the claim, the hardware seems up to the task,
Yeah.
and there's a clear path to using it. But you mentioned healthy skepticism earlier. What are the caveats? How should we think about this without getting carried away and thinking, the quantum apocalypse is here?
Well, first, always remember, classical methods don't stand still. People will keep improving classical algorithms and hardware. That 3.2-year estimate might shrink. But the achievement here is tied to a specific measured quantity, OTOC2, where the signal strength is defined. And it hits a known weak spot in classical methods, those off-diagonal terms. The advantage isn't vague. It tracks specific, hard-to-simulate features.
And the big question everyone asks, does Willow break my bank's encryption today? Is RSA dead?
No, definitely not. Let's be super clear. This has basically zero immediate impact on cryptography. Shor's algorithm, the one that breaks RSA, needs huge, fault-tolerant quantum computers, millions of stable qubits. We are nowhere near that. Willow is powerful, but it's not that.
Okay.
However, the sources did mention an interesting, maybe nearer-term security angle, using these echo protocols for verification.
Verification, how?
Imagine a company offers quantum computing time in the cloud. How do you know they're really running your calculation on a quantum computer and not just faking it with a classical simulation? Well, these time reversal echo protocols are so sensitive to the underlying quantum dynamics. It's thought that only a real quantum system could actually execute them properly and produce the expected interference pattern. So running an echo protocol could become a way to authenticate the quantum hardware itself, sort of proof of quantumness.
Huh, interesting. Okay, so for you listening, let's recap the reasonable way to think about this. One, the advantage shown here is specific. It's for a scientifically relevant task studying information scrambling. Two, the advantage is tied to known classical bottlenecks, those off-diagonal interference terms in OTOC2. And three, the path to actual use seems pretty clear. Things like Hamiltonian learning, maybe helping out in fields like spectroscopy or material science.
Yeah, and that points to what researchers should be doing now. If you design quantum algorithms, maybe think about time reversal not just as a trick, but as a core building block. And for the classical simulation experts, the challenge is laid down. Can you find better ways to handle these off-diagonal turns? Or maybe develop hybrid approaches, use classical for the easy parts, and let a small quantum device like Willow tackle just the really hard interference bits. That's how the field progresses, right? Less hype, more cumulative building.
Okay, wrapping this deep dive up. If you take away just one sentence, maybe let it be this. The quantum echoes algorithm effectively turns time reversal into a powerful microscope, and Google's Willow chip is finally stable and precise enough to actually use that microscope effectively.
Yeah, that's a good summary. That combination gives a verifiable quantum advantage backed by numbers classical experts have to take seriously. And it shows a plausible route from just running benchmarks to creating tools that could actually help scientists working on spectroscopy or trying to figure out material structures.
And as you often say, the gap between demonstrating something like this and people starting to use it can be surprisingly short sometimes.
It can, so here's the provocative thought, the challenge maybe. If you run a lab dealing with complex molecules, materials, anywhere NMR or similar methods are crucial, you should probably be thinking about a pilot project. Right now. Team up with a quantum lab. Compare your standard techniques, your confidence intervals, against what you can get from this OTOC2 Hamiltonian learning approach. The real test is, can you nail down some tricky, weak interaction that's been bugging you for months? Can you do it in a week using this? That's when a research paper becomes real-world progress. That's the challenge to the field.